right, physics, don't forget you have a test on Friday, so you will need to log in by 11 a.m. and upload the video. We will do a Zoom call. I will be sending, I should be either sent or will be sending the invitation for that. Today, what I'm going to do is start into chapter 12. Now, if you want to stop this video right now and wait until after the test to watch it, that's perfectly fine, because I'm not going to make this due until Monday. So if you kind of want to wait until after, that's okay with me. If you want to take Thursday as a study day and just leave this until later, that's okay with me. You can decide when you want to watch this. It's one of the bonuses, I guess, of doing it this way. You can watch it when you want, but the work won't be due until Monday, so you decide. But I am going to head into chapter 12, and I'm going to look at the first part of section 12.1. Chapter 12 is on universal gravitation. So we are going to start talking about planets and satellites and space and all of those things. As we go through this, we might do a Zoom meeting or two with it, just to talk through some of the theory of it a little bit. And you guys, again, can have feedback on that, whether that's something you want to do or not want to do. It's fine. But this is really going to be talking a lot about space and things like that. So there is some theory in this, and again, I'll be uploading the PowerPoints for you. So the first part of this section is really a history lesson. There was a video that I would show part of. I'll see if I can find it again, because I switched computers and lost all my links. So I'll see if I can find it. If I can, I'll put the link in there for that as well. It's just a little bit about the history. It won't be on a test or anything, so if you want to watch it, you can. If you don't, it's up to you. But for some of you who kind of like that aspect of it, you're more than welcome. So in previous science courses, you learned about the Ptolemaic system for describing the motion of the planets and the sun. The system was developed by Ptolemy in 151 to 127 BC, and it was really complicated because it was geocentric. In other words, it put the Earth in the center, and it had all the planets and the sun and the moon going around the Earth. Now, the reason why it did that was because of all the religious beliefs at the time, that it really was heresy to say anything else. It was just assumed that God made the Earth the center of everything. We were his creation, and we were the most important thing, and so therefore that's how it worked. So this idea stuck around until in about 1543. So that's like it's like 1500, a little bit more than 1500 years. So it's stuck at, like, the whole Earth as the center of the universe was around for a really long time. Nicholas Copernicus actually was the one who came up with the system that said, no, the sun is the center of the universe and everything goes around it. He was the one who came up with that, and it was a whole lot simpler. It explained a lot of things, and all the math they were trying to figure out worked a whole lot better when the sun was actually the center of the universe rather than the Earth. The Copernican system, though, was rejected by the clergy of the time, and you kind of have to think about how the world was working at that time. The church was also the government, so everything was very, very intertwined. And so if the people in charge of the church decided that something should be this way, they were able to make that law. So not just, hey, I believe this, but hey, now it's law. So it says, they actually put Galileo on trial because he supported Copernicus. He said Copernicus is right. Galileo said Copernicus is right. The math works. Like everything just works this way. That got the government really upset. And they actually put him under house arrest for a while, put him on trial, and he was convicted of heresy because he agreed with Copernicus that the sun was the center of the universe. But there was another guy around this time. His name was Tycho Brahe. And he came up with a system that was kind of a middle ground between the Ptolemaic system and the Copernican system. And what Brahe said, so it's called the Tychonic system, is what it's called, or the Tychonic system, depending on what pronunciation you go with. He was Danish. He was a Danish nobleman and an astronomer. And there's a picture of the system that he proposed, but he actually, what he said was that, let me see if I can explain this right. The Earth is still and is the center of the universe, and the sun and the moon both go around the Earth, but then the planets, the other planets, they all go around the sun. So Earth is still in the middle, the sun and the moon are going around it, but while the sun is going around the Earth, all the other planets are going around the sun. So that's what he said was happening. Now, when you watch some of the history, and like I said, if I can find the documentary, I'll put it up. And we usually only watched a piece of it. I'll tag whatever time it was, but Brahe was actually kind of a jerk. He was a nobleman, and he would get money from other noblemen, and he would get paid to go and talk at different functions and stuff. Back then, scientists were almost treated like rock stars are now. They were famous, and everybody wanted to have them at their parties, and everybody wanted them around. But Brahe would like pick fights and stuff at parties. He was known as the guy with, I can't remember, the golden or the bronze nose or something. There's a couple of different stories out there about whether he lost his nose in a fight or he got sick and it, like some kind of flesh-eating bacteria took it. But anyway, he was not really known as a good guy. But what he did do was he did a lot of work in terms of astronomy because he was able, he had a really isolated castle kind of in the middle of nowhere, and he could watch the heavens and things. So I'm just trying to find my place. For more than 20 years, he kept detailed records of the positions of the planets and the stars. He actually cataloged more than 777 stars and kind of the path they take. Can you imagine watching 777 stars and watching them every night in the sky? And in 1572, he discovered a new star that he named Nova. It was actually one of the very few supernova ever found in the Milky Way galaxy. He also discovered a comet, and demonstrated that it was not an atmospheric phenomenon like they thought, but instead it was something that was actually orbiting out in space. In addition to making observations and collecting data, Brahe designed and built the most accurate astronomical instruments of the day, and they have some diagrams of those in the book. Now, Brahe was an astronomer. What he was not was a mathematician. So what he would do is he would make all these observations, and he hired mathematicians to do all the calculations that went with it. One of the people that he hired was a guy named Kepler, Johann Kepler. And he hired him, and just a year later, Brahe dies. And again, there's some controversy over how he died and Who was responsible? Was it natural causes? Was it not? Was Kepler responsible for it? There's some questions there that we actually don't know the answer to, because according to research and according to some of the notes and things they've found, Brahe wasn't real nice to Kepler, and Kepler would come to him with these ideas and these theories, and Brahe would either dismiss him or he'd steal his ideas and kind of pass them off as his own. And so when Brahe dies, Kepler got all of the notes, all of the work that Brahe had done. So Kepler kind of benefited once Brahe died. So with his wealth of astronomical data and his ability to perform meticulous mathematical analysis, Kepler actually discovered 3 relationships that describe the motion of planets. And today we call them Kepler's laws. There are 3 of them. They're obviously important. They're laws. So Kepler's laws are really important, and they will be listed for you in your PowerPoint. Obviously, something you should know. All right? So there are 3 of them. The first one that Kepler said planets move in elliptical orbits with the sun at one focus of the ellipse. So, again, this was actually controversial, which sounds kind of silly to us today. Why is it controversial that things don't go in a circle, they go in an ellipse? Why is that a big deal? It's actually a big deal because we talked way back, like in chapter 1, about the fact that the circle was the perfect shape. And remember, I can't think of his name right now, but you know who I mean. He said that everything on Earth was made up of 4 different essences, and then there was that 5th celestial one, and that's what kept all the heavenly bodies in their path, was they all were in this crystalline sphere, because the sphere was the perfect shape. And so again, it was assumed that Earth was the center and that everything moved in a perfect circle around that. And Kepler said, well, not only is Earth not the center, but things don't move in a circle. They move in an ellipse. So he's kind of blowing a lot of the thinking of the day right out of the water. And he said that the sun is always at one focus of the ellipse. If you're in grade 12, we talked about an ellipse and what the focus was. So in an ellipse, there is a major axis. There is a line that goes from the center of the ellipse to the 2 longer ends, all right? A focus point is a point somewhere on that major axis, so that if I draw a line to any 2 points on the ellipse, and I add up the length of this line and the length of this line, they're always going to add up to be the same thing. So even if I did like this and this, it's a constant. All right, so that's what he said. But don't worry too much about the sun is at one focus. That should still be in your definition, but if you're kind of like, that's not such a big deal. The sun is at one focus in the ellipse, but the big thing is that they move in ellipses, and that was a big thing to say at that point in time of history. Law number 2, he said there's an imaginary line between the sun and a planet sweeps out equal areas in equal time intervals. So think about it this way. So say here is your sun, all right? Because of the way gravity works, and if you haven't seen the movie Apollo 13, I encourage you to. It's a good movie. Apollo 13 was about a trip to the moon in the late 60s that doesn't go very well, and they actually get stranded out in space, and they have to try and get themselves back to Earth. One of the things they do is to get back to Earth, they slingshot themselves around the moon. They use the moon's gravity almost as a slingshot, because the closer you get to the sun, or the closer you get to any body, the closer you get to the moon or whatever, the gravity is more intense. So that means the object speeds up. So it actually goes faster around this way and then slows down as it gets further out and then speeds up, slingshots around, and that's how that works. All right, so it's going faster over here than it is over here. So what he said was, just a second, I'm just trying to find it. So the planet moves along the arc of each section in the same period of time. So it's moving faster here. So if we take a certain time interval, like a month or a week or whatever, and we say it goes, the planet goes from here to here, it would go a much further distance. If we take the area of that section, okay, and then we take that same time interval, whether it was a week or a month or whatever, and we look at when the planet's over here, how far does it travel? Well, it's not going to travel as far because it's moving slower, right? So it's going to go a narrower amount. But if I find the area of this section and I find the area of this section, so say that was 1 week's motion and that was 1 week's motion, the area of the two sections would be the same. So the way they word it is this: an imaginary line between the sun and the planet sweeps out equal areas in an equal amount of time. So it might be a different shaped wedge, but it's going to have the same amount of area. The last law, law number 3, is actually a formula. And I don't know what I did with my thing. There it is. The last law, the third law, is actually a formula, and it says the quotient. So that means we're going to be dividing. The quotient of the square of the period of a planet's revolution, so the amount of time that it takes a planet to go around the sun once, a planet's revolution, the square of that around the sun, and the cube of the average distance from the sun, so the average. So it changes depending on where the planet is, but they're saying if you take an average of how far away that is, so how far away that is, we'll call that R. If you cube that, okay, the cube of the average distance from the sun, you always come up with the same number. Doesn't matter what planet, doesn't matter what heavenly body. If you take the cube of how far it is away from the sun, divided by the square of its period, you always get the same number. You always get this same number. Now, Kepler wasn't able to figure out what that number was. He didn't have enough information to figure out what that number was, but he said it's going to be a constant, which I don't know how he knew that. He's way smarter than me. I don't know how he knew that, but he figured that out, but he didn't have the information to figure out what this constant was. So this kind of got around the scientific community, and they were all, so now all the astronomers, all the scientists are now really interested in, what is this K? What is this constant? Everybody wanted to know what it was. Again, remember, scientists at the time are pretty famous people. They're usually rich, or at least if they're not rich, they have a rich benefactor, someone who's funding them. And so if you could be the first one to find something, that was really huge at that time. I mean, it's big now because we have things like the Nobel, Prize in Chemistry and that kind of thing for good discoveries. But back then, it was even more prestigious. So typically in research, the scientist makes some observation that leads to a hypothesis, and then the scientist tests the hypothesis by doing experiments, getting data, and then comparing the results to their hypothesis. The development of Newton's law of universal gravitation actually happened in reverse. Brahe's data and Kepler's analysis of the data were just really sitting there ready for Newton to use and to test his hypothesis about gravity. But like I said, Newton wasn't the only one of his time looking for this, because this K is really what we now call the universal constant. So Newton wasn't the only one looking for this number. He wasn't the only one trying to figure all this out. In fact, several scientists were racing to see who could find the correct explanation first. One of those scientists was an astronomer called Edmund Halley. And if you've heard of Halley's Comet, that's the guy. He found and named Halley's Comet. It's named after him. So he was a pretty famous astronomer at the time as well. Halley and others, based on their calculations, had proposed that the force between the planets and the sun decreased with the square of the distance between the planet and the sun. In other words, the further away the planet, the less the gravity, basically, is what they were saying. However, they didn't know how to apply that concept to predict the shape of the orbit. Halley decided to put the question to Newton. He decided, I'm gonna ask Isaac. I'm gonna see. Halley first met Newton in 1684 when he was visiting the University of Cambridge, which was where Newton was working at the time. And he asked Newton, he said, what type of path a planet would take if the force attracting it to the sun decreased with the square of the distance from the sun. So in other words, what path would it take if there was less gravity when it was further away and more gravity when it's closer up? And again, we now know that that's an ellipse, because we know when it's close, there's a lot of gravity, so it goes faster. And then as it gets further away, it slows down, but it gets pulled back towards the sun, speeds up, and then slows down again. But they didn't know that at the time, right? This was all theoretical. So Halley said to Newton, what would that path be? What shape would it take? And Newton immediately replies, well, it's an ellipse. And Halley said, how do you know? Like, what's your proof for that? How do you know? And this is my favorite response ever. To me, this makes them seem like real people and not just some people in history books. Because here's what Newton said. He said, oh, I made that calculation a long time ago, but I lost my notes. I can't find them anywhere. Doesn't that, that sounds like me, right? I did that, but I don't know where I put it, right? That's what Newton said. He literally said, I figured it out a while ago, but I can't find my notes on it now. And so Halley was like, dude, you need to find those. Like, those are important. You should, if you can't find the notes, go do the calculations again. So that is what Newton did. He went back and he redid all the calculations so that he would have the proof that things actually move in an elliptical pattern. And 3 months after Halley said, go find your notes or redo them or something, in only 3 months, Newton had written an article called On Motion, and Newton continued to improve and expand on that article, and in less than 3 years, he had produced one of the most famous scientific books ever. It's the one that has his 3 laws of motion that we've studied in it. He talks about this planets go in elliptical patterns. He talked about a universal gravitational constant, all kinds of things that we now base a lot of our math and our physics and our knowledge of the universe and how it works. We base it off that. And all because Halley said, dude, go find your notes. I just find that funny. So it says, possibly Newton was successful in finding the law of universal gravitation because he didn't just think about gravity and law of gravitation in terms of what happens out in space. Have you heard of that story where Isaac Newton was sitting under an apple tree and an apple fell and he went, "Oh, gravity"? Um, it's I don't know if that actually happened or not, but the point is that he was looking at gravity as working the same on Earth as it does out in space. Gravity is the same, and so if I can apply the rules here, then the rules shouldn't change just because the location changes. Whereas other scientists were thinking that gravity out in space was very different from gravity here on Earth, when in fact it's not. And so what Newton reasoned was that the same attractive force that existed between the sun and the earth was also responsible when an apple fell to the earth for attracting the apple to the earth. And he said, if the apple is attracted to the earth, then the earth must also be attracted to the apple. That's that law of action-reaction, right? For every action, there's an equal but opposite reaction. So he said, if the apple is attracted to the earth, then the earth also must be attracted to the apple. And he was able to use those concepts and think about it in such a way that he was able to figure out things that other scientists at the time were not. So Newton therefore proposed that the force of gravity between any two objects is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. And he called this the law of universal gravitation. And again, this is a formula. This is a formula. So he said that if you want to find the force of gravity between any two objects, whether they're out in space or whether they're here on Earth, if you want to find the force of gravity between any two objects, it is proportional to their masses. So you would multiply mass 1 and mass 2. You'd multiply the two masses together. And inversely proportional, which means it's a ratio, so it's dividing. Inversely proportional to the square of the distance between their centers. So if you have mass 1 and mass 2, the distance between their centers is called r. And so it said inversely proportional to the square of that. Now, he knew that there was a gravitational constant that needed to be worked into that constant that Kepler had talked about. There had to be that. But again, he wasn't sure what it was. But he put a letter there to represent it. But he didn't actually know what it was, what the value of it was. That wouldn't be found out for a while. But I can tell you now because we know now. So this big G is called the universal gravitational constant. So by the way, this is just force of gravity is. So this is force of gravity. Now, it's not force of gravity of something falling to the earth. That's mass times gravity. This is force of gravity between any two objects. If you are standing beside someone, there is a force of attraction between the two of you. It's not huge because your masses are not huge. But there is a force of attraction between any two objects. So this universal gravitational constant, G, is 6.67 times 10 to the negative 11th. Now the unit for that is really crazy. It is newtons times meters squared over kilogram. But you don't really need to worry about that because what's going to happen is it's going to end up canceling everything out and you're going to end up with newtons in the end. All right? Okay. I think I'm going to stop there. We could do the math that goes with this, but I don't think we're going to. I'm not going to give you anything to do other than to watch this video by Monday. That's all you have to do, have it watched. Okay, and Monday we'll do some math with that. So you had a little bit of a history lesson today. I'm going to post this and maybe a link to one of the documentaries I mentioned. Have a good day. don't forget, if you're watching this on Thursday, you have a test on Friday.